The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let's start. For the first question, you can answer what is tuple. You can go through that later. Can a tuple contain a list? What do you think? Can a tuple contain a list? Yes, it can. So we'll go through the examples later. And let's see this first example. We have two tuples. The tuple B contains tuple A as well as a list. OK, so it can probably, let's say. Let's print the resource too. OK, so for the first example, we try to access the elements 0 and 2 of the tuple A. And later we use -1 to access which element? OK. And 0 is the first element, of course. And remember, now we are using like 0, 1. It's like we are accessing the, it's now, OK, what is tuple B? It's a two-dimensional tuple. Yeah, exactly. It has a list and a tuple inside. So the first element has first element is a tuple, and the last element is a list. So now it's sort of like two-dimensional. But if you look at the second, or first element of it, the MIT word, that doesn't have any dimension. Does it? It's a string. So you can again access, but not this way. But still you can access. And we are using this notation to access a portion of the list, a part of the tuple actually here. It's called slicing. So here, 0 to 1 gives you which element? Just one element, right? It's the first element. 0 to 2 gives you 1 and 2. OK? This is an interesting usage of the slicing. This is used to access the whole tuple. Now you might wonder why we need that. We could just, the handouts are here. So why we need to copy, or why we need to access the list through the colon operator like this? We'll look at that later. It's very essential when we have lists. For the time being, it's OK. Tuples are immutable, so it doesn't have a special usage. But later on, we'll be using it. Then if you look at this part, this is the most interesting part. How do you iterate through a tuple? You use a for loop, and you call item in tuple, the element in tuple. The element is initialized with every element when it goes through the iteration. At every iteration, it will be instantiated with the corresponding element in the tuple. But you're using the same name anyway. It's item. This is equivalent to accessing the tuple like this, going one by one in the range and accessing the corresponding element in the tuple. So this is a simpler way to access that. Do you have any questions in that part? Oh, yeah.
But for that part, don't usually if you have a range, you have to place the best ones in the name for the thing because it's not.
OK, that's correct. So the thing is, OK. Suppose a tuple has 3 elements. So for example, in this case, tuple A. How many elements are in the tuple A? 3 elements. So what will be the length of tuple A? 3. But what would be the range? 0, 1, 2, right? Yeah. So you have to type 0 to 3. Mm-hmm. So that's why I put length. OK? That is 3. OK?
So if you just say range like the tuple, it assumes that the first one.
First is 0. If you don't specify, it's 0. Yeah. Okay. Now let's go through the list. So if you go through the questions, what is the difference between a list and a tuple? Yeah. What is the difference between a list and a tuple? Anyone? Yeah.
Tuples are immutable.
Okay, lists are mutable. And because it's mutable, it has like special functions to like access the elements, add elements, and like modify the list itself. How would you add an element to a list? Suppose you have list A. How would you add 3 to this list? Okay, list.append. Okay, that's good. Okay. How would you remove the element from the like top of the list or the last element? How would you remove this 3 from the list? This one? Let's see. We know how to check the specification of a function, right? Sorry. So it's not the right function, right? Because it says it removes the first occurrence of a particular value you pass in to that function. Okay, there's another function, which is called list.pop. That removes the last inserted value. So it pops from the top. Okay? So remove can be used to remove a particular element. So here, suppose we want to remove 1. So we could say list A, remove 1. Okay. So in this example, actually, I have commented out this line. This would be an error if I execute. Why? Why it will like give an error? It doesn't exist. Great. So the problem here is we can't access an element in the list unless we explicitly assign something or create something. But suppose we want to pass a list of 10 elements to a program so that it can assign values on the fly and it can modify. Okay? So how would you pass an empty list of 10 elements? Okay. The problem is, if you're passing something like this, you need to know how this list should be instantiated. So you should know what are the initial values of these elements. Okay. Suppose you want to create a list of 10 zeros. Then the easiest way to create the list is this. So it will create a list with 10 elements. But if you don't want to waste memory, or if you don't want to like keep anything particular, you could do something like this. Now this will create a list of empty lists, and there will be 10 such empty lists. Okay. And you could pass this list to a program so that you will assign the elements. Okay. You can iterate through the list the same way. But lists are interesting. Why? They are mutable. So they can be actually used to create interesting mathematical objects, for example, like matrix. So how would you create a matrix using lists? Any ideas? How would you create, say, 2 by 2 matrix? if you consider this example, this creates a matrix 4 by 2, right? So there will be like 4 rows and 2 columns. But how can you go and access the inner element or inner matrix? So if you suppose you want to access 2, 3, that is the third row, then how would you access? How would you call M? M3. M3 gives you 2, 3. Suppose you want to access the 3 in the 2, 3. Then?
Wait, why,
Sorry. Yeah, you have a
why does
question.
M3 give you 2 green sets before?
Oh, sorry. My bad. Yeah, okay. This is like computer science, not maths. You got it, right? Why it's not 3, it's 2? Because
Yeah,
of the
I thought
index.
you were talking about 3.
Yeah, that's fine. So like I'm asking now, like how would you access the 3 in the 2, 3 box?
So I'm to do another.
Parentheses?
Another bracket.
Yeah.
Okay, yeah. That is more. So you can access like you can access matrices like this. Okay, great. We are on time. Okay. So this actually gives you a summary of functions, I mean essential functions. For example, the pop I explained earlier. Remove removes a particular element. Extend, that's interesting. Can you tell me what it does here? The method extend on list. Okay. What does that method take? It takes another list. So which means it's going to merge the list you are passing with the list you are calling the method on, that is LA, right? So it's going to combine the results. Let's see. So this corresponds to this. So 2 lists are combined. Okay. So these methods are actually useful, right? Because you don't have to write yourself. Most of the things you can easily do. Now the question is, why Tuple didn't have these methods? Why? Why we didn't have these methods for tuples? They are immutable, so you can't extend, you can't append. So when you extend, what will happen? It's going to create a new tuple. Actually, you can do that, but like this. For example, you have tuple A, which is 1, 2, and suppose you have tuple B, 3, 4. If you want to combine them, how would you do? Tuple A plus tuple B. Okay, that concatenates. This operator is overloaded for tuples. Okay. So lists are mutable, so you can do all of these things. Let's look at a few other examples too. Okay. Okay, there's an interesting part here. Lists are mutable, that we understand. But how these lists are actually stored in the memory? For example, suppose you have a list LST, sorry, 0, 1, apple. How do you think it's stored in the memory? So you have 3 elements, but these elements are actually not stored in the list itself. They're actually in the memory. 0, 1, apple. But you have the pointers to those lists, to those elements. So actually, you can modify these values without changing the list itself, because the list actually points to this part, the container. So in this example, you have list A and B, but the list B actually contains list A. Okay? Since list A is immutable, you can go and change it. So here first you print list A and B, but you're going to change list A's 0th element. Okay? After changing the element, the list A becomes this, with its first element changed to 88. Okay? Fine. What do you think the list B would be? Okay, let's print. It contains the 88, right? The modified value. Why? Because list B actually had a pointer to list A, which again had pointers to other elements. And we modified this value to 88. So you are still accessing list B. Okay? The pointers are not changed. That we can see here in the second example, the problem of aliasing. So we have list X, and we call it by list Y as well. And we are now changing the list Y. Sorry, we are changing the list X. But it's going to affect list X as well as list Y. See? Because it's just a reference. The actual object is this. You can call it by 2 different names. It doesn't matter, but the actual object is here. That's where we need this operator. So if you just point, OK, for example, we had list X. If you just assign list Y to list X, it's not going to copy the elements, just going to copy the reference, which means list X and list Y both will be pointing to the same object. If you want to copy these elements and put in a new one, say list Z, then we need to copy 1 by 1 every element. For that, we can use this operator. It's called full slicing. It's not going to modify the elements. It's going to copy the whole list of elements. Great. In the same line, there's another small example that tells you how to cast a list into tuple and a tuple into list. So you had a tuple, 1, 4, apple, zigger, and you cast into list. Now the type is list. It's a very simple operation. Can you do that yourself? How would you do it? Like if you want to write a function to cast, how would you do that? You go through element by element and add it to a tuple. and concatenate two tuples, right? So I guess you can write probably as a homework, try that. Like try how to convert a list to a tuple without like explicitly calling the casting function. Okay. Similarly, you can convert a tuple back into list. So it's pretty straightforward. And suppose you are getting an input from the user as a tuple. Then suppose you want to make it as list. You don't have to write your function. You can just call this casting operator, right? So it'll be like, it will save some time. OK, great. Let's go through the dictionaries now. So we have the third data type, dictionaries. Oh, you didn't get the second one? So we have another data type, dictionaries. And why do we need dictionaries in the first place? Do we need another data type? Can't we like just get away with tuple and list? Yes, because you can actually make a dictionary out of lists. And Professor Eric Grimson went through that in the lecture. If you want, you can come and ask in the office hours. But first, try whether you can do that yourself. But the problem is, actually, not just the dictionaries, but other high-level data structures are actually available in Python as like built-in data structures or as classes, just because like they will have these methods on these data structures implemented. So it would save some time for us. Plus, those methods are guaranteed to be like state of art. For example, if you want to go through all the lists, then the search function or the lookup function that you write may not be like that efficient, right? But they might use those efficient algorithms in the standard implementation. So it's why you should always like look for the standard data types. If you can't, you can like write yourself one. But it's good to use the available data types so that like they will have these efficient methods implemented. OK. So in this list, dictionary, we have like two elements. One is key, one is value. OK? So these keys actually have a special property. What is that? The keys should be an immutable object. So you can actually have a tuple as a key. You can have a string as a key, but not a list as a key. So you need an immutable object for the keys. What about the values? They can be anything. Values can be even a dictionary. It can be a list. But the keys must be immutable. Do these keys need to be like unique? Yes. No? OK. The problem is this. Dictionaries have the same type, same structure. This is a key. And this key points to a place in the memory. Suppose you call it key A. OK? If you assign another value to key A, that will actually replace the content in the memory, right? So that's why keys are going to be unique. It's by construction. By the construction of the dictionary, the keys are going to be unique. Because you have to, if you want to assign something different, you have to call it by a different key, call it by a different name, say key B. What about the values? Do they need to be unique? No, of course. Otherwise, no use of key and no use of dictionaries, right? What is the order of the items stored in the dictionary? Can you give a guarantee? Like in lists, items are stored from 0 to the length, right? Length minus 1, actually. What about dictionaries? Actually, you can't guarantee the order, but you can modify the order. Okay. So thing is, first, if you look at this example, first we have the staff dictionary. And when I print the length, it gives me 3. Fine. Then I'm like doing few things. First, I changed the address by calling its key. And dictionaries are mutable, so you can change the values. Then also we are adding a new element. Fine. If you want to add a new element, you call it by the key that you want to assign. If the key already exists, it will just modify the value. Otherwise, it will create a new key and add the value. You can also check whether this particular element is in the dictionary. But this must be the key. Whatever you are calling here should be the key, not the value. It won't search for the value. It will search only for the key, presence of a particular key, because you access the values through keys. Again, here, if it is not in the list, actually, I'm adding an element. OK. To compare, in the list, suppose I have a list 0, 1, 2. If I want to check whether 1 is in the list, how would I check? Do I have to go through element by element? No. There's a shortcut. If 1 in list, right? If I want to check whether 1 is not in the list, if I want to negate this, I would write if 1 not in list. We just ignore the verbs. It's pretty much like English. Okay? We just remove the verbs. Okay. In the dictionary, we do the same thing through keys. If key A in, OK, I'll call it, say, D1. OK? And you actually call or you search for the keys, not the values. OK. That's an interesting part here. If you want to modify the order, actually, I told you that the order C earlier, we couldn't guarantee the order, right? It was not the order we typed, because it starts with Hamian. Because we added at the end, actually, right? So actually, you can't guarantee the order. But we can sort it. But how do we sort it? We call the keys, and we sort the keys. Because remember, every values, if you want to access a particular value, you access it through key. Actually, if you call the dictionary, it doesn't know where these values are. It has to go to the key to access the value. So if you want to do something on the dictionary itself, you can do that only on keys. So if you want to sort the dictionary, you sort it by keys. So you call the keys function, sorry, it's method for the dictionary. So it returns the list of keys, and you sort them. Okay? This is called chaining method. So I have chained the methods. I've added like 2 methods, right? I call keys. This first part actually returns you a list of keys. Then you sort them. Yes?
It doesn't look like they're in alphabetical order.
Oh, on this? Sorry. Let's see. Oops. OK, let's see. OK. Oops. OK. Now they're sorted. OK. What was the problem? What was the problem there? Why it wasn't sorted?
You have to do it in 2 lines.
Sorry?
You have to like call up the keys and then sort it in a separate line.
Okay, the problem is with in the logic. When you call this function method, you're actually sorting the keys returned by this method. You're not actually going to sort the dictionary itself. You're sorting only the list that was returned, right? The list of keys. Although the dictionary is mutable, it wasn't sorted. Do you see the problem? So that's why when I called keys equal to staff.keys, I'm getting a list of keys. Then I'm sorting that list, and I'm printing that list. But if you want to go in a particular order, or if you want to access the dictionary in a particular order, what could you do is you could do something like keys is equal to staff.keys. Then you can store keys. Then for k in keys, you can go and iterate now, right? So you can say print k and staff k. Okay? So you can do this. But actually, the Python provides a way through iterate both keys and value pairs. That you do by calling both elements over the method items. The items return a list of key value pairs. If you call d1.items, you get a list of key value pairs. You see that? And we are going to iterate through individual elements. So first we start with this, second this. Okay? So there's a simpler way to access every element in the dictionary. Great. Okay. Now we are at the interesting part, recursion. Okay, what's the principle behind recursion? Anyone? Oh, what's the idea of recursion? Yes?
Well, it calls itself until you get to a base case, and it saves a lot of money.
Yes. The idea of recursion is if you have a problem, try to express the problem in a simpler version of the same problem. So if you want to find, say, factorial n, try to express it in terms of factorial n minus 1. So you could keep on doing this till you come to, say, factorial 1, for which you know the explicit answer. Right? So you try to express the problem in its simpler form. It will be useful like in many cases. Actually, in your next piece that you will have the problem. But be mindful. What like makes it possible for you to use the recursion? Only if you can express in terms of the simpler version. Otherwise, you can't. This is probably quite like the induction you might have studied, mathematical induction. I don't know whether you studied in high school, but it's quite like that. OK. So there are two parts in recursion. The first one is the base case. So for a factorial problem, we can express the factorial, say, nth factorial as n into n minus 1 factorial. Okay? So this will be our recursive case. So what is our recursive case? Suppose we want to define a function factorial n. Okay? So what will be our recursive case? No, I'm asking the recursive function. What will be that? N into factorial n minus 1, right? And you just return this. What will be our base case? If n is equal to 0, we know factorial of 0 is 1, right? What is factorial of 1? 1. Okay? But why in this program we didn't have that particular line? Why we didn't have n equals 1? Why we didn't have that? It will always go 0, right? Because you can express 1 in terms of 0 as well, right? So you don't need to actually write this explicitly. Why? Because your recursive function only depends on its previous value. So you need only one value in advance, which means you need only one value for your base case. But, so you can understand this program, right? I'm not going to go through that. But anyway, like when you write a program, always check its base case. So you have to start with factorial 0 for this case. Okay? And check one by one. Then you would know whether the program is running correctly or not. So always start with the simpler case. But remember in Fibonacci series, okay, for Fibonacci series, can you give me the recursive function? Yes. What is Fibonacci series? Okay, yeah, that's correct. So return, say, f of n minus 1 plus f of n minus 2. What is the Fibonacci series? You start from 0, you add these elements, so 1, you add last two elements 2, you add last two elements 3, you add last two elements, right? Okay? So you add last two elements. So if you want to find f of n, you return f of n minus 1 and plus f of n minus 2. But here, since you have like two elements, or you need to access two previous elements, you need to define your base case accordingly. So for your base case, f of 0 is what? Actually, that depends on whether you start here or here. Okay? You could do this. I'll go through an interesting recursive example. Okay. It's called recursive exponentiation. So actually, you can do an exponentiation through recursive multiplication. Suppose you want to find 3 to the power, say, 10. Then how would you do that? You start by like expressing it in terms of its simpler version, right? So it will be 3 into 10 to the power 9. Sorry, 3 to the power 9. Okay? So if you want to find the nth power of number m, you would say m into m to the power n minus 1. Okay. So now you have your recursive case. What is the base case? Yes, if n is equal to 0, in Python you would test this by 2 equal signs. If n is equal to 0, then what? Return 1. Okay. Why we have only one base case here? Sorry?
Is it always best?
Yes, and because you're accessing only one previous element, right? Unlike Fibonacci series. Okay. Similarly, if you want to multiply something, okay, here what we did is like we replaced this operator by recursively using this operator. Okay? Can you do the multiplication by recursive addition? So can you replace this operator by this operator? Yes. So how would you do this? For example, say 3 into 5. So how would you do it here? Tell me. What would be this?
Three plus
3
3 times 4.
3 times 4. Here? Come on. Okay, it's simple, right? I'm insulting you. Okay. What's the base case? That is interesting. What is the base case? If n is equal to 0. Okay. If n is equal to 0, that is 0, but that's fine. But there's another problem. The problem is you don't know whether these values are positive or negative. So you can't just keep on adding like this. This will work if it's positive. But if it's negative, actually you have to check, which is sort of tricky. It's just if you want to use the same recursive function. Otherwise, you could have like had a if condition here. If say n is greater than 0, do this. Okay. Else if you multiply n by minus 1, you negate that, so it becomes positive, and do it the same way, and then like reverse the answer, right? So you could do that. But if you want to do it in the same recursive case, then you have to follow this. If you have any questions, come to the office hours on that. The final example is the Hanoi example. Okay, this is very interesting. So here we have 3 towers: source, target, and buffer. Suppose you have like 3 disks. You want to move them from source to target. And you can always have a smaller disk on top of a bigger disk. Then how would you move? Okay? So can you express this problem in its simpler version? So now you have 3 disks. You want to move them to target. So can you express it in a simpler version? Come on. Just in plain English, how would you do that? Without looking at the program. Because Python is very verbose, so if you read the program, you get it in English. So, any ideas? Okay. We had to anyway move the last disk to target, right? But that's the hardest part. So before doing that, you have to like move this somewhere else. So let's move it to buffer. Done. How would you move this? Now you can move it to target. Okay. Now what should you do? Okay, sorry. Yeah, okay. Now what would you do? You can only move this to the buffer, right? Not the target. Okay. So we made some mistake earlier. Remember? The problem is because we didn't think recursively. Okay. Let's think recursively. Source, target, buffer. Sorry. Suppose we have only one disk. Then you can simply move it to target. Okay? So our condition is if there's only one disk, just move it to the target. So if n is equal to 1, we always move source to target. Okay? Suppose you have 2. Then what would you do? You move the top one to buffer. Okay? So move source to buffer. Then you move the next disk from source to target. So now it's source to target. And finally, you move it from the buffer. Right? Now we have a very nice recursive case. If you have 2, we move from source to buffer, then source to target, then from buffer to target. So if you look at this example, I'm checking if n is equal to 1. If it is 1, just I'm moving the from source to target. If it is greater than n, what would I do? And the first assert statement is just there to make sure n is greater than 0. Otherwise, like it's meaningless, right? You need to have disks. You can't have like negative disks. Okay. So what would be the next step? If you don't have, if you have more than one disk, suppose you have 2 disks, then what would you do? You move the top disk or whatever on the top to the buffer. For this simple example, it was just one disk. But suppose you had more disk on top of the last disk, so you would have moved all of them to buffer. You don't have to worry how you move it, but you have to move it anyway. Okay. After moving that, you can leisurely move this big disk to the top, to the target. Sorry. Okay. Finally, you bring back all of them here, right? Okay. For your first operation, from source to target, you have to move all of them, right? The bulk. You could have used target as your buffer. Okay? So that's why in this line, I'm using source as source, but the second argument, which should have been the target, is now buffer, because my current target is buffer for the top n-1 disk. But my buffer is now the target, okay, because I can use the target as buffer for that movement. Then I moved from source to target, the last big disk. Okay? For that, I can use buffer as my buffer. Okay? Then finally, I bring back from buffer to target using source as my buffer. Okay? So the thing is, if you want to handle a recursive problem, you can do it in 2 ways. One thing, you can start thinking like how to express this problem in its simpler version, like how we thought about the Fibonacci series, for instance. Or else, you can start from its base case. the most fundamental situation. So here it's n equal to 1, but this doesn't give you enough context, so you go to the next level. N is equal to 2, and you have the answer, right?